Welcome back for week 7 of the engine performance class, virtual. Uh, Today, I want to continue on with the lessons we were talking about last week. But first, I do want to mention, midterm grades went out, and I did say in the email I sent along with that some of you didn't do very well, and there's really two reasons why someone at midterm wouldn't do very well. In the lecture, nobody that took the test did so poorly that they're in trouble of failing. So people that got an F at midterm, the reason for that is you decided for some reason not to take the test. I encourage you to talk to me in the lab and figure out what you can do about that. So I did get an email or two. I prefer that we have a face-to-face conversation about that. If you got an F or a very poor grade in the lab, most of the time when people get a poor grade in one of my labs, it's for one of two reasons or both. Reason number one, poor attendance. So, there's a total of 150 possible points for the semester, 10 weeks, 15 weeks rather, 10 points each. So every time you miss a class, you're dropping 10 points right off the top of your grade. So you miss a couple classes in half a semester and your grade's going to be pretty bad. The second reason why people do poorly or fail in my labs is they don't do don't give me lab reports. So you're really putting yourself at a disadvantage if you're not giving me a lab report every week. So if you don't know why you got a bad grade, then you should definitely ask me about it. Maybe I made a mistake. If you do know why, because of one of the reasons I just told you, then you really need to talk to me. It's still early enough in the semester that there's a lot of points left out there that you can still get. So, but you have to do it. You can't continue along. If you continue along the same path you're on now, your final grade is going to match your midterm grade. So, okay, so much for that. The next thing, let's just review where we were at. So I need to share the screen here. Let's see. And what I've got is, let me get rid of my video here so you don't have to look at me. I'm going to go into the engine performance class on Blackboard as usual, and under lessons, just to make sure you know where to find stuff, right? So if you're watching this by now, there's a 7th lecture up here, and that's what you're actually watching. So obviously I hadn't recorded this yet at the time, hadn't posted it to Blackboard, so that's why it only says the 6th. If we look down, we're in Module 2. So Module 2 is where any videos that I'm showing you or any slides I'm showing you come from. So we were in this first batch of slides right here. And in this first batch of slides, we were pretty far along, but I had shown you some videos too. So we were talking about ignition system operation. We started talking about the conditions in the cylinder and how they affect the ignition system. If any of this is news to you, go back and watch the last video. What's the ignition system for? We need a hot spark that lasts long enough and happens at the right time. It should be a strong enough spark that it can jump the gap even when the conditions in the cylinder are really difficult, like high pressures or lean air fuel mixtures. And you need to realize that the air fuel mixture takes a fixed amount of time, so as the engine goes faster, we need to get it started sooner or it'll happen too late. So that's why we need spark advance. We have mechanical advanced systems, or we used to. They're pretty much all electronic now, so it's up to the computer to decide when to fire the spark plug. It has all the information it needs. It has all the sensors, all over the engine telling it, load and RPM and everything like that. So it only makes sense. Then we talked about the ignition system components, the low voltage or primary circuit, the secondary circuit, which is the high voltage. over the years has gone from 20 or 25,000 volts to more modern, greater than 50, possibly a lot greater than 50. And a primary circuit, like I say, low voltage battery ignition switch wiring. This is the thing here. Let me just annotate. The two things we really want to talk about is a triggering device. Okay, so this is some piece of equipment on the car that lets the computer or an ignition module know where that crankshaft is, that it's, now it's time to fire, or this is, the next cylinder has come up near top dead center. And then the other thing, of course, is some sort of ground side switching device. Now, when we watched the video on the old-fashioned, 1950s, 1960s, early 70s, the point-style ignition system, we watched that video last week. The switching device was the actual contact points, and the triggering device was just a bump, bumps on the distributor cam that were rotating around that would push the contacts open, thereby, causing the spark to happen at that exact time. Okay, let me get rid of this here. So over the years, we've gone through different types of switching devices. We started out, like I said, with points. Those are no longer used, so you may go through your entire career and never run into a set of points. Depends on what you're working on, but chances are pretty good you'll never run into them. Points were replaced in the 70s, I'd say, by an electronic ignition module, or sometimes you'll see it called an ICM, an ignition control module. These were standalone electronic modules that had, some advanced features. They could, retard the spark. They could control what's known as the dwell, or how long the primary current flows, but they were pretty much dumb electronic devices. They couldn't take a whole lot of, information in. And then there were variations. There were electronic spark timing systems that, there were separate modules maybe that fed a signal to this ignition module or altered the timing. That stuff has pretty much all gone away too. So any relatively modern car, the ignition system, the coil or coils, is going to be controlled directly by the powertrain control module or the engine control module. So here's a question. What's the difference between an engine control module and a powertrain control module? And the simple answer to that is powertrain control module also controls the transmission. So the entire powertrain, engine and transmission, rather than just the engine. Over the years, some cars have had separate transmission control modules or no transmission control because it was a, it was not an electronic transmission. So these are the three switching devices we've seen. Early on, points, they were replaced with electronics, which of course, no moving parts, no wear, big improvement. Also, more current was allowed in the primary, so that increased the power of the spark. And then to simplify things, our PCMs got much more sophisticated. Early ones maybe had 20 or 30 wires going to them, or the Fords had a 60-pin connector on it. And then, now they have over 100. So that PCM is all by itself controlling, ignition, fuel, all the different emission control systems, variable valve timing. It's controlling the transmission. It's controlling probably any kind of cruise control. So a lot of functionality in one module, including the ignition system now. So depending on what year car you're working on, it may or may not have an ignition control module. Probably not nowadays. As far as triggering devices, you know, back in the point style one, the thing that triggered it, the thing that pushed the points open, right, was this distributor cam. So when that cam, just a high spot on the cam, pushed the points open, that caused the coil primary magnetic field to collapse, and that's what generated the spark. So then early on, you know, I was mostly domestic vehicles, so what I could say is that General Motors and a lot of other manufacturers used one kind of triggering device. They used a magnetic pulse generator. Now, there are other names for this. Let's see if I can write this down. You might see VRS, which was variable reluctance sensor. Now, reluctance is something that a material has if it's attracted to a magnet. So, you know, in the lab, most labs this week, I demonstrated a lot of this stuff to you. There were a couple labs where there was too much actual work and I didn't get to do the demo, so that probably will happen, you know, this coming week. I've seen the name PM generator for this type of sensor. It's the same thing. You know, it's putting out little pulses of electricity using the same technology we talked about with coils and transformers. It's using electromagnetic induction. So we have a magnetic field and we have wire within that magnetic field. And when we disturb or move that magnetic field, it causes electricity to happen in the wire. That's what's being fed into the ignition module or the PCM to tell it where the crankshaft is. So crank sensors work this way, camshaft sensors can work this way, wheel speed sensors can work this way, vehicle speed that runs your speedometer, that can be a magnetic pulse generator or a magnetic pickup. So I mentioned GM and Ford, and so the reason is Ford went with something called a Hall effect device. Now, a Hall effect, you know, let me just really simply, it's a little chip, and that chip had 3 wires, right? So up here, power. Down here, ground. This is the output. And then over here, a magnet. And if the magnetic field is allowed to hit this Hall element, okay, let me see if I can make it say that. Hall element, right? Over here, is a magnet. Right? So if this magnetic field is allowed to hit the Hall element, then the Hall element is on, and we have an output here. Okay. If the magnetic field is taken away, so make that go, then our output is taken away and this Hall element turns off. So this actually works more like a switch. So key difference here, right? The magnetic pulse generator is just what it says. It's a generator. It creates electricity, and it creates alternating current. So if you were to look at it on a scope, you know, you see this alternating current. The Hall effect doesn't create any electricity, right? So it takes electricity that you've already fed it, and it just turns it on and off. So the output to that is, you know, it's on, then bam, it's off for a while, bam, it's back on, stays on, off. And so these transitions where it switches from on to off or off to on can indicate to the computer the position of either the crankshaft or the camshaft or a distributor. So what you're looking at here is really two different ways. I'm not talking about the points anymore. Just we brought that up just to show you how it used to work. But two different ways right here. Magnetic pickup or a Hall effect. Two different ways to do the same thing. And that same thing is to generate some sort of a signal to feed into an ignition module or a PCM that indicates that the crankshaft or the camshaft or the distributor has moved to the next tooth on a wheel or the next slot on a Hall effect. So two different ways of doing the same thing. Now, when I first started talking about these, I said it was kind of a GM Ford thing. So this magnetic pulse generator, right, that was kind of, the General Motors solution. Their way of doing it. The Hall effect, that was kind of a Ford solution. And, that was early on. So I just want to say, that doesn't mean that there were no other car manufacturers using magnetic pulse generators, and it doesn't mean there were no other car manufacturers using Hall effects. It doesn't mean that at all. But this is two major manufacturers and the difference in the way they did things. Accomplishing the same result, these devices have the same purpose in life, just two different technologies to do it. Now, 2020, you'll find a GM car with a Hall effect. You'll find a Ford car with a magnetic pulse generator. You will find cars that have some of each. In other words, maybe the crank sensor is a magnetic pickup and the cam sensors are Hall effects. Or maybe the crank and cam are Hall effects, but the wheel speed sensors are magnetic pickups. Or maybe the cam sensor is a Hall effect. The crank sensor is a magnetic pickup, and the wheel speed sensors are Hall effects. So you see, anytime you're trying to pick up rotational speed or position, these are the two technologies that they rely on. And when I'm going to say they're interchangeable, I don't mean you can take one off and put the other in its place. They have different requirements. The Hall effect requires voltage supplied to it, where the pulse generator creates its own. And the computer that's designed for a Hall effect would have no idea what to do with the AC signal from a magnetic pulse generator. But they do the same thing, right, essentially. And we talked about the secondary circuit components, the ignition coil, the secondary windings of the ignition coil. So the ignition coil is part of both primary and secondary circuits. High tension wires, maybe. It says on most engines. Now, I have to update this slide because this is not really a true statement anymore. Probably when I made this slide a few years back, it was. I would say now on most engines, the wires have gone away and we have coil on plug. So on some engines, distributor with distributor cap and rotor. Yeah, not too common nowadays. I've seen them in the shop this year. Maybe one. I see maybe one or two a year. Some older vehicles, especially trucks. Trucks tend to be slower for the updated technology. And of course, another key component of the secondary circuit is the spark plug. This is where, this is where the actual thing that we need to do happens, right? We need to create a spark. It happens at the spark plug. So secondary windings of the coil is where the high voltage is created. The wires, if they exist, bring that to the spark plug, and then the spark plug is where the high voltage is high enough that it allows electricity to jump over an air gap. So this is kind of where we left off, electromagnetic induction. We talked all about this. We had videos on it. It's the way a transformer works, so that includes an ignition coil, but it's also the way that magnetic pulse generator works. Same thing. Magnetic field, wire, put the two together, you get electricity. The key is they have to be moving, right? So the magnetic field has to be moving, or the wire has to be moving, or the magnet has to be moving. Just the wire and the magnetic field have to be moving in relation to each other. So what happens in every ignition system that you'll ever see? Some sort of ground side switching device closes. So that used to be points, then it was ignition module, now it's pretty much the computer, right? So that completes a circuit on the side, the coil primary. So current flows through the coil primary windings. And a magnetic field builds up. So how long does this take? Milliseconds. At some point, excuse me, I should probably edit that out, but I won't. At some point, the magnetic field stops growing, reaches its full strength. Again, we're talking just milliseconds here. And we call that coil saturation. It's the field's not going to get any stronger. So now we wait. We sit with this magnetic field built up in the coil until the computer receives a signal from some sort of a triggering device that it's time to fire that coil. So on a signal from that triggering device, the ground side switching device opens the circuit, interrupting the current flow to the coil primary. This causes the magnetic field to collapse inward across the secondary coil, creating the high voltage in the windings, the secondary coil windings. One line I skipped right over here, this concept of dwell, not something we really think about. We used to have something called a dwell meter, and we could adjust the points, and that would adjust how long current flowed through the coil primary. Now that's all controlled inside the computer or the ignition module. So on the point style, we saw it, battery voltage applied to the positive side of the coil through a resistor. The resistor would limit the current through the system for longer component life, but of course that also reduced the intensity of the spark. So usually during crank, when we're trying to start, that resistor would be bypassed. There would be 12 full battery voltage supplied to the coil, and then this mechanical switch that we called points would complete the primary circuit. When the cam pushed the points open, that would cause primary to collapse and secondary across the secondary, and we'd get about 25,000 volts. Sometime in, say, the 70s, I'd say mid-70s, I'm thinking, 1974, 1975, all of a sudden every car we were seeing had done away with the points. There were still cars out there that had them, there were trucks that had them, and, all kinds of other things, tractors, boats, whatever, but cars in general, we're getting rid of them. And so away goes the points, away goes the distributor cam that pushes them open, and in its place, the electronic ignition module, so that's the switch, and then some sort of a ignition pickup, magnetic or Hall effect, and that would feed into the ignition module, for positioning, crankshaft position. So the ignition module then would perform the switching function using a transistor, opening the coil primary on a signal from the ignition pickup. So let's talk a little bit more about the pickup styles. The magnetic pickup, we've kind of beat this idea to death, right? Uses induction. So permanent magnet surrounded by a coil of wire, and I've got a picture on the next slide or a drawing. We have something called a reluctor. So usually that's a wheel with teeth on it, and so that reluctor is being rotated by the engine, and every time a tooth passes by the magnet, it causes the magnetic field to wobble. And since the wire is sitting there in the middle of the magnetic field, the magnetic field is wobbling uh, across the wire, causing a little bit of current in the wire. So that's the signal that's being created. That small current's applied into the ignition module. There's some additional circuitry, but the key is, the switch in there is a transistor. And so pretty simple. Feed pulses from that sensor into the ignition module, triggering it to keep firing the coil. Here's a little, a little drawing that this is an old Ford style, because I forgot to mention they used to use magnetic pickups before they went to Hall effects, right? So, so here you have a magnet, and attached to that magnet this hunk of steel or iron, right? So the magnetic field is on this piece of metal. See if I can get rid of that. Whoops, that's not the right thing. There we go. All right, so notice, two wires and wrapped around a coil here. So that's all there is. This is not fancy. There's no fancy electronics inside this. It's just a magnet with wire wrapped around it. So that by itself does nothing, right? If I just wrap wire around a magnet, I don't get electricity in that wire. How do I get electricity in that wire? I got to make the magnetic field here move around in relation to that wire. How do I do that? Well, every time one of these teeth, right? There's a tooth, there's a tooth, there's a tooth, there's another one. Every time one of these teeth passes by, and it's pretty close by, passes by this hunk of iron or steel that's a magnet, the magnetic field from this magnet stretches out towards that tooth, reaches out towards it, and then as the tooth moves away, that magnetic field falls back towards the magnet, right? So, the magnetic field is going, that way, then it's going that way, that's going that way. So what's happening? The electricity is doing the same thing. As the tooth is approaching the magnet, electricity flows in one direction in that coil. And as the tooth is moving away from the magnet, electricity flows in a different direction in that coil. And so what you're looking at down here, right, is what you would see on an oscilloscope. So here's 0 volts. We're talking alternating current. So we have, sometimes we have positive, up here, and sometimes we have negative, that's down here. So the voltage, and because of that, the current is alternating. And so for every tooth, what do you get? You get these spikes. There's a spike, there's a spike, there's a spike, there's another one, another one. Or you could say it the opposite. You get 0 volts, then again you get 0, then you get 0, you get 0. So the computer or the module can just look for those spikes and know that every time there is one, that represents another tooth. And every tooth represents the next cylinder that needs to be fired. So every time there's a wobble in that magnetic field, that means a tooth has passed by it. Every time that happens, a little spike comes out. If the ignition module is keying on those, then, or the computer, then it knows, okay, it's time to fire the coil. A Hall effect, on the other hand, I already said this, but it's there for the same reason, but it works completely different. So here's what you need to know. A magnetic pickup is going to have 2 wires, generate its own voltage. It's going to be alternating current. So if you're testing it, you got to take an AC voltmeter. A Hall effect doesn't generate its own voltage, right? So it's fed, might not always be 12 volts, but it's fed power and ground. And then the third wire, so that's a key if you're looking at it. It's got 3 wires, it must be a Hall effect. The third wire is the one that turns on and off. So you feed 12 volts into this thing. What comes out? 12 volts, 0 volts, 12 volts, 0 volts, depending on whether the magnetic field is blocked or not. So I'm just trying to decide. I have a video. Let me do that rather than try to explain this too much myself. So we'll look back here on module 2. Down towards the bottom here, I have a link to a video on Hall effects. Let's look that over.
How to ease an irritated prostate in 3 easy steps. Number 1, eat chocolate.
Can't wait to skip that. Okay, there we go.
Look for high quality dark.
Alrighty. This should be better than the ad.
Hello, Dan Milowski here from howtomechatronics.com. In this video, we will learn what is Hall effect and how Hall effect sensors work. The Hall effect is the most common method of measuring magnetic field, and the Hall effect sensors are very popular and have many contemporary applications. For example, they can be found in vehicles as wheel speed sensors, as well as crankshaft or camshaft position sensors. Also, they are often used as switches, MEMS compasses, proximity sensors, and so on. Now we will go through some of these sensors and see how they work, but first let's explain what is the Hall effect. Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So, the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879. The basic Hall element of the Hall effect magnetic sensors mostly provides very small voltage of only a few microvolts per Gauss, so therefore these devices are usually manufactured with built-in high-gain amplifiers. There are two types of Hall effect sensors, one providing analog and the other digital output. The analog sensor is composed of a voltage regulator, a Hall element, and an amplifier. From the circuit schematic, we can see that the output of the sensor is analog and proportional to the Hall element output or the magnetic field strength. These type of sensors are suitable and used for measuring proximity because of their continuous linear output. On the other hand, the digital output sensor provides just two output states, either on or off. These type of sensors have an additional element, as illustrated in the circuit schematic. That's the Schmidt trigger, which provides.
Okay, so this second one, the digital output, is more likely what you're going to see as an ignition pickup, a crank sensor or a cam sensor.
Hysteresis or two different threshold levels, so the output is either high or low. For more details how the Schmidt trigger works, you can check my particular tutorial for that. An example of this type of sensor is the Hall effect switch. They are often used as limit switches, for example, in 3D printers and CNC machines, as well as for detection and positioning in industrial automation systems. Another contemporary applications of the Hall effect sensors are measuring wheel speed or RPM, as well as determining position of crankshaft or camshaft in engine systems. These sensors are composed of a Hall element and a permanent magnet, which are placed near a toothed disc attached on the rotating shaft. The gap between the sensor and the teeth of the disc is very small, so each time a tooth passes near the sensor, it changes the surrounding magnetic field, which will cause the output of the sensor to go either high or low. So, the output of the sensor is a square wave signal, which can be easily used for calculating the RPM of the rotating shaft. Thanks for watching, and for more tutorials, visit my official website howtomechatronics.com.
Okay. All right, so what we're seeing here is, the switching device and the triggering device that are commonly used, either a magnetic pickup or a Hall effect. So we'll switch gears now and start talking about the various designs that, types of ignition systems that have been around through the years. One thing I forgot is I do have a little video on electronic ignition systems that it's similar to the one we saw on breaker point systems, but it's updates and shows you how they've changed. So let's go back to here, and I'll just show you. We're still right. We're still in under lessons down here, module 2. I have something called electronic ignition system operation. There's no sound with this, so I'm just going to play it. Maybe I'll talk a little bit over it. Remember, we had the point style initially, and we just saw that video. So here we'll see we're going to get rid of the points and in its place put in an electronic ignition module, and then we have to add in some sort of triggering device. So the triggering device, of course, they're calling it an armature. You could call it a reluctor. That particular thing is a magnetic pickup. I can see there are 2 wires. There could also be a Hall effect there instead. Anything to signal the ignition module, once per cylinder. And then the rest, I mean, it works the way we're used to. So I'm just going to let this go. You can read. I think you'll see some coils that do better than 50,000 volts nowadays too. This is obviously an old distributor style ignition. We're going to look in a minute at some other kinds that do not use a distributor, so they don't have this rotor. Because of the air gap between the rotor and the distributor point, they're calling it, that leads down to the spark plug. Some of the spark energy is used up jumping that little gap too, and so that takes away what's left for the spark plug itself. So there's an electronic distributor ignition system, probably going back into the 70s, 80s, could be 90s. So the other thing I want to talk about now, we did not look at every slide here. Just so you know, you can look. I may cover this later, but down towards the end of these slides, we talk about how transistors operate, and I don't want to get into that right now, but basically a transistor is a high-speed switch that's very sensitive, and that's the core, or the base, the most significant part of an ignition module, or anything in the computer that turns things on and off. So what I really want to do under Module 2 here is move on to the additional slides. And here there's a lot of review, about ignition system operation, stuff we just finished talking about. So what I'm more interested in is talking about configurations, different designs of ignition systems. So they all use an ignition coil, at least one ignition coil. Some use one for the entire engine. Some use one for every pair of cylinders. Some use one for each cylinder, but they all use at least one coil. And we already know the primary circuit's the low voltage. Secondary circuit is the high voltage. So in a distributor ignition, we have, coil wire, distributor cap, rotor, spark plug wires, right? In a distributor-less ignition system, we get rid of the cap and rotor here, right? So they're gone. And in a coil-on plug, we get rid of the wires completely. So all of these systems are in existence. All of these systems are, in use, but the distributor ignition is getting more and more rare. You may go quite a while without seeing one. The distributor-less ignition, there's a couple different kinds, so we'll talk about those. Those you're going to see. So we have in a distributor ignition a single coil, and in a waste spark system we have coil packs. Another possibility is coil per plug, where there's one coil for each spark plug, but there is still a little wire. And then there's coil on plug, where the ignition coil is mounted directly on top of the spark plug. So I want to talk about waste spark. This can be the most confusing for people. So picture a 4-cylinder engine, and I want to talk about cylinders 1 and 4. Cylinders 1 and 4 move together on the crankshaft. Cylinders 2 and 3 move together on the crankshaft. So whenever cylinder 1 comes up to top dead center, so does cylinder 4. Whenever cylinder 4 comes up to top dead center, so does cylinder 1. So what's the difference? The difference is they're not on the same stroke in the 4-stroke cycle. If the number 1 cylinder is coming up on the compression stroke, then the number 4 cylinder is coming up on the exhaust stroke. Next rotation of the engine, then it would be the number 4 cylinder coming up on the compression stroke. Number 1 would be on exhaust. So they keep switching roles, they keep switching spots, but these cylinders that move together are known as companion cylinders. So in a 4-cylinder engine, for example, 1 and 4 are companions, 2 and 3 are companions. So the way the coil configuration is, we'll see it in a minute. Let me see, I think it's, right, let's just look right here, okay? This is a 6-cylinder engine, very, very similar idea. You have an ignition coil here, you have an ignition coil here, and you have an ignition coil here. So we call this this entire thing, right, a coil pack. So it's a pack of coils. And let me get rid of all this nonsense here. So notice, we'll just concentrate on, coil number 1. So this first coil is connected to cylinders 1 and 4. These are companion cylinders. They're moving together. And so when the coil fires, current's going to flow down one wire across the spark plug gap. So it's flowing in that direction across the spark plug gap, from the center electrode to the side electrode of the plug, or the ground electrode. And then it continues in a circuit from the ground electrode of this plug back to the center electrode and back to the coil. So this is here, let me complete the circuit, right? Through there, and this is completed through the engine, the metal of the engine, the cylinder head or whatever. So this is a loop. So when the coil fires, both plugs fire simultaneously. Get rid of that. All right, so these companion cylinders, every time one spark plug fires, so does the other. So another terminology here. There's something called the event cylinder. Now the event cylinder is the one that's on the top of its compression stroke. And when that spark plug fires, it creates a combustion process, right? And begins the power stroke. The other cylinder, the other companion that's on its exhaust stroke, we call that the waste cylinder. And in the waste cylinder, the spark fires, but it really doesn't do anything. There's nothing in there to burn. So we have companion cylinders. Every time they come to the top, the spark plug fires. Half the time, it causes a combustion process to start. The other half the time, it's just wasted, depending on whether it's the event cylinder or the waste cylinder. So they just take turns. Going to this next, slide. So if cylinder number 1 is the event cylinder this time around, next rotation, cylinder number 4 is going to be the event cylinder. Then it's going to be cylinder 1, then it's 4, then 1, then 4. So even though the plugs both fire, only one of them actually does anything. So let's see. Is there anything in here I missed? Just that fourth dot point, very little energy is required to jump the waste cylinder spark plug. So most of the energy goes to the event cylinder plug. Just remember a little earlier in our discussion about spark plug firing requirements, having pressure in the cylinder increases the amount of energy it takes to make a spark. So on the exhaust stroke, you got the exhaust valve open, you have no pressure in the cylinder, and it does not take much energy to jump the plug gap. So it goes to the one that's on the compression stroke, just by default. Okay, so a waste spark system, the terminology, coil packs, we have positive and negative plugs, but we don't care. They're probably, the same part number. The spark is jumping one direction on one of the plugs and the opposite direction on the other plug, but again, we don't care if it's jumping the gap, it's a spark, it'll light the air fuel mixture. We don't care which direction it's jumping the gap in. So that's a waste spark coil configuration. You've got some advantages over distributor ignition. There's no cap and rotor to be replaced. You take out, anytime you take moving parts out of a system, you make it more reliable. You don't lose the energy of the spark having to jump from the rotor to the cap. So it all goes to the spark plug instead. The downside of this system is it still has spark plug wires, and spark plug wires are they're a point of failure. So that leads us into what came next, what came after waste spark. Not saying that waste spark no longer exists, but what came next is getting rid of the spark plug wires. So here's a picture of a GM 6-cylinder waste spark coil pack. in this setup, actually the ignition module is underneath these coils. They're sitting right on the ignition module. So here's all your power and ground, and your input, to and from the computer for spark advance, and your input from the crank sensor and possibly the cam sensor. They all feed into this ignition control module, which is down here underneath these coils, and they just screw onto it. There's leads that come out of it. So moving on from waste spark, we have two different systems here. I have coil on plug, coils mounted directly on top of the spark plug. If a coil fails, it only affects the cylinder that that coil is connected to. So that brings up a good point that I didn't mention back when we were talking about distributor ignition. Distributor ignition, one coil, and that spark is being distributed out to various cylinders. If that coil fails, you have a no start. You have no spark on any spark plug. In the waste spark system, so we go back to this one, right? If this coil fails, cylinders 1 and 4 are both going to be dead. So that 6-cylinder engine is going to become a 4-cylinder engine. It may still run. Not that you should drive it with 2 dead cylinders. Let me just mute this a minute. Okay, sorry, my phone was ringing, and it does not ring, the home phone. So back to the point here. If that coil fails, we lose 2 cylinders. If we go to a coil on plug, if a coil fails, just 1 cylinder. So troubleshooting becomes pretty easy. If I have a car that comes in with a misfire, one of the easiest things I can do, usually it just involves a wiring connector and 1 small bolt, well, 2. I can swap 2 coils, right? So let's say a car comes in and has a P0302. That's a cylinder 2 misfire. I take the number 1 and number 2 coils and swap them, and take the car out and drive it, and now it has a P0301 code. What does that tell you? That tells you that the misfire moved from cylinder number 2 to cylinder number 1 when you moved the coil from 2 to 1. So you know right away that you've got a bad coil there. You can do the same with a spark plug if you suspect the spark plug's a problem, right? It's not quite so simple to do usually with injectors if you suspect a bad injector. So we'll get into all that kind of diagnostic stuff later. But coil on plug, really nice for ruling out or confirming bad coils. So coil per plug systems, they have a coil mounted near the spark plug with a tiny little coil wire. So I'll show you pictures of that. And then some systems have a coil mounted directly on a plug with a short wire to another plug. So it's actually a waste spark system, but the companion cylinders are wired to a coil that is installed on one of those plugs. And then there's a wire to the second one. And then there's dual plug systems too. So let's look at these pictures, right? This is your basic standard coil on plug ignition coil. Some of them have more circuitry in them than others. So if you look at this and there's only 2 wires in the wiring connector right here, then all of the circuitry is outside of the coil. And this is just simply a coil. If you look, and there are 3 or 4 wires here, then there's actually some electronics built into the coil itself. Probably going to be more expensive. here is a coil per plug or a coil near plug. You see them called both things, all right? So up here, the coil, right? Here's your low voltage, primary circuit connection. So that's going to be back, and then the other wire is going to go back to the ignition module or the computer. And then you have a little spark plug wire going down to the spark plug. I think the reason for this, honestly, is if you look at where the spark plug lives, this is the exhaust manifold. And something you should understand about exhaust manifolds, they are pretty much the hottest part of the engine. This is where the hot exhaust gas first comes out of the cylinder. So to put a coil in that environment, right here between two ports of the exhaust manifold, it may not live very long, right? So the coil is up here, of course, on top of a valve cover. Isn't exactly ice cold area either, but certainly not as hot as right next to the exhaust. So typically, when you see a coil on plug, like this, right? This is right down through the middle of the valve cover, nowhere near the exhaust. And so the valve cover basically has holes in it, and the cylinder head has holes leading down into the cylinder. So this is an example off of General Motors 5.3. And I think what they've done is they've taken what used to be a distributor, well, that was never a distributor, but the basic V8 design, used to be distributor with spark plug wires coming from a distributor cap and, terminating here at the spark plugs. And then they went to waste spark. There were still spark plug wires coming from somewhere else and terminating, same place right here at the spark plug. Now you want to go with a coil for each cylinder. It's just too hot down here for the coil, so you still got the little dinky wires. So this is one that's kind of strange. We have here one output from the coil, so that's going to go directly down on top of a spark plug. And then from this terminal of the coil, you're going to have a spark plug wire coming out to a second spark plug. So obviously when this coil fires, this one fires and this one fires. So what we have is a waste spark system. But instead of having plug wires to both, we have a plug wire to one cylinder and the other is a direct connect. And then this over here would be the low voltage, battery voltage connection to it. And then here, this is off a Ram truck, 5.7. This is a dual coil, so this does not go to two different cylinders. This is just two spark plugs in the same cylinder, which is not a completely unusual configuration. It's been around. It was on some Ford 4-cylinders. They had dual plug ignition. This one has it. A lot of airplane engines have it. I know my airplane engine has it. 2 plugs per cylinder. And the old Mazda rotaries, in fact, they don't have cylinders. They have combustion chambers and rotors, but they had 2 spark plugs in each combustion chamber. And the timing was not necessarily identical on those two. They had 2 different distributors and 2 different coils, and they were kind of weird. But this one here, it's a coil that, let me bring up the annotation. So, you're going to have that same loop, like through one spark plug and then back to the coil through the other. So it's just going to be a circle going around, and both plugs are going to fire. So they're going to fire at exactly the same time, but they're both in the cylinder during the combustion event. So it's just going to give better combustion, better lighting of the air-fuel mixture. All right, let me stop this a minute. Let's turn my camera on. Okay, I think that's about it for today. I think I've thrown enough stuff at you that when you see these things out in the shop, or when we are out in the shop, you can ask me about them. But we're going to see. I don't know about distributors, but we're going to see everything else every week in the shop. As soon as you open a hood, you're either going to see that waste spark ignition system, coil per plug, coil on plug. You may see that dual plug setup. You may see a distributor. That's just less likely. That's all. And these are not tied to any particular car manufacturer. In other words, you're going to see both domestic, Asian, European cars that over the years have had distributors. They've had coil packs, waste spark systems. They've had coil on plug. So this is kind of a universal thing. You'll see all these different configurations. It mostly depends, I would say, on what year the vehicle is. So the newer it is, the more likely you're going to see ignition coil directly on top of the spark plug. The older it is, the more likely you're going to see a waste spark system with coil packs and coil wire, or spark plug wires. And when you get even older, you may see some distributors. So a lot of this depends on where you work and what kind of stuff you're working on. Many of you will never ever see a set of points, except for that one I showed you in the shop on that old distributor that I have laying around. I know if you work on industrial equipment, it could be old airplanes, boats, things like that. They don't age out as fast as cars do. So you're going to see old technology on that kind of stuff. But if you're working on cars, particularly if you're working in a dealership, mostly what you're going to see is coil on plug now. And we'll see what happens next. So that's about it for this week. I'll see you in lab, and we can talk about this stuff. I can show you whatever examples I can find of it, and then we'll move on to other stuff.